Good morning, everybody. Oh, I see only one student show up. Let me see who's there. William, good morning.
Good morning.
Good morning, Mariana.
Good morning.
Remember, we're down to 4 students on Tuesday. I was a little bit worried. What happened to students now?
Oh yeah, I joined in at the beginning and then like I emailed you. It kept
Yeah.
down. Yeah. So
Signals are not stable. Yeah.
yeah, but I don't know about everyone else.
But I don't know. I tried to upload the YouTube recording, Zoom recording. And guess what? I tried the whole afternoon. I think the internet traffic was really bad. So, after I tried the whole afternoon, it went through. So the recording is there. Okay.
Yeah, I think I saw it last night. I
Yeah.
watched a little bit of it.
Yeah. And today the pre-lab is due for Grignard.
Mm-hmm. Yeah.
Yeah, do you think you guys can handle it? Hello? Good morning,
Yeah.
Andrew.
Yep. Yeah, I think I can handle it.
So Andrew, what happened on Tuesday? Were you having problem?
No, Tuesday I stayed up all night. Tuesday to get all the work done because I had to go to work in the morning. Then afterwards,
Yeah, just too
fall
many
asleep.
deadlines, huh?
Yeah, I fell asleep literally at 11, and then it was just a lot of stuff due this week. Like, not just for this class, it's a lot.
Yeah, I heard from other students complaining. I shouldn't say complain. That they're all making the instructor aware of the situation.
Yeah, like.
Yeah, luckily I teach 2 courses this semester, and for me it is just transitioning for 2 courses. But the thing is, I need to help other instructors too. In the course that I coordinate, actually 2 courses I coordinate. Oh my goodness, life is upside down. Our life is really upside down.
Yeah, we missed like a week and a half before spring break. And so all the classes want to catch up on that week and a half. So like there's so many different projects and stuff going on. It's like kind of nerve-wracking to keep track of it. And then like
I fully understand. So I guess one student, George wrote to Dr. Lopez about the workload. Okay, and according to Dr. Lopez's reply this morning, he says he will postpone the deadline for a peptide report. Okay. And then he gave me a couple suggestions about other activities about our class. I'll talk about this later. So let's see, is everybody here yet? No, there's 6 of you. I'm happy. It's a lot better than last time. Okay, let me open Dr. Lopez's schedule now. Okay.
Yeah.
The revised schedule. Hold on.
Oh shucks. Where the hell is my phone?
All right, now let's look at what is happening here. So this week, okay, I finished 50% of the lab lecture, and today I can complete the theoretical introduction, and then I think for today you're able to submit the pre-lab without major problems, okay? I'm on schedule. I stick to this schedule carefully. But the thing is, my lecture is ahead of Dr. Lopez's lecture. So I heard during this week, on Monday, Dr. Lopez was actually reviewing the NMR. And he told me in today's email, he will get this Grignard reaction started next Monday in his lecture. Okay, so you will learn models, more more theories or more models associated with Grignard reaction, introducing the new chiral center. Okay. And so, okay, I'm not behind. I'm on schedule, and since I've noticed you just submitted this Aldo report, and then next Monday, according to this old schedule, even though it was revised, okay, another peptide report. And then you will write Grignard report, then another report, you take midterm, and then oral presentation. Oh my goodness, my head is spinning just by looking at it. And so I think George, is George here?
Yeah.
Yeah, George. Yeah, I was informed by Dr. Lopez the peptide report will be pushed by 1 week, but this is not being finalized officially. So we wait for his second revised schedule, okay? It should be, yeah, it should be sent to us this weekend. Yeah, well, I told the other class on Monday and Wednesday section, because we're a small group here. Total number of students in my 2 lab section is down to 21. So there are only 22 of us making noise. So I appreciate the fact, you know, students actually write emails to Dr. Lopez in addition to my request. Okay, we push him together, and so he's willing to postpone the dipeptide report. This is really good news to all of you. But what I worry now is, okay, now you postpone this, and then there's another report, and you still have to take the exam. You still have to do your oral presentation. Okay, in the next 3 weeks, you're supposed to perform full speed, okay? And so I want all of you to be prepared. You get the 1 report postponed doesn't mean you have an easy life for the, you know, for the rest of the semester, okay? So watch out for this. You want to plan ahead, okay? All right, okay, so let me start my lecture. Okay, now can you open this reaction, open the page of the Grignard experiment. Okay, this is the reaction. Okay, I cover a little bit mechanism and information already about this Falking-On model. And let me see who's on board now. Oh, okay. Okay, so I want to know if you still remember Falking-On, and did you take time to study or try to work on this reaction after my first lecture on this model? Are you able to make prediction which compound is supposed to produce in majority?
No.
Well, well, Andrew, you were not there, and I wonder the rest of the class here. Were you able to get on the reaction at all? And just get get the Felking-Alm model sketch on the piece of paper and then work on the possibility of making a tag with a nucleophile. Is anyone here willing to share the experience? And I will reward you with a bonus point.
I tried to do it, but I'm not sure if I'm right with which one I think will be dominant.
Okay, but were you able to draw the structure?
Yes, the projections and then the 3D structure.
Right, according to this model. So between 2A and 2B, were you able to make prediction?
Yeah, I made a prediction.
And what is your answer?
I said 2B.
Yeah.
2B, you think 2B is your answer?
Yes.
Okay, then, you know, why don't I do this, okay, William? So let's see if you're doing the right thing. It seems to me, you're probably not getting the model sketch on the piece of paper correctly, okay?
Okay.
All right, so let me review a little bit. Okay, now let's take a look at the Felking-Alm again, okay? The model says, okay, you are very similar to this example, okay? We have this Grignard region instead of, this is another region which is nucleophile, okay? And chiral center, the first chiral center is already available from one of the carbon, okay? And you're doing the nucleophilic attack with this methyl group, and you will produce another chiral center, okay? Originally, it was just a carbonyl carbon. Okay, so you will be doing this attack, okay? And I want you to look at this molecule now, okay, with phenyl group, hydrogen, and the methyl group. Okay, you know phenyl group compared to hydrogen, this is much bigger. Phenyl group compared to methyl group, you know this is the biggest group of all, right? And in using this Felking-Alm model, you just need to watch out for which one is the biggest group. And so the largest group from the reaction right here, since it is phenyl, okay, so I will write this phenyl group, the largest group, 90 degrees vertical to the carbonyl group. And you want, always, you want the carbonyl group pointing up with oxygen pointing up, right? Okay, and this hydrogen here, you just draw 180 degrees. You know, you want to draw this hydrogen 180 degrees from the carbonyl group. Okay, and this is all coming from the view angle. Okay, the view angle. If you look at the molecule from, okay, can you follow my hand right here? If you look at the molecule from this angle, follow my hand from this angle, you will see carbonyl group pointing up and hydrogen pointing down, okay? All right, so the model says, now we have this 3 group and phenyl groups being the largest. So you have 2 choices. You either draw the phenyl group 90 degrees on the right-hand side of the carbonyl group or on the left-hand side. So there will be two possibilities in terms of the conformation or your Newman projection, okay? When you rotate the single bond, you get this conformation. And so you work on the model from this angle and determine the nucleophilic attack, okay? And I think I said that on Tuesday for you to determine pathways of the nucleophilic attack. And I told you there will be 4 pathways. When you do the nucleophilic attack, you want 107 degrees angle to the carbonyl group. Okay, so William, are you able to do the same? Okay.
Yeah, I have the 2 ones and then the 4 ways they can add on, but I think I may have been changing, I may have been adding them wrong.
Okay, don't worry, I'll come to that point later, okay? Okay, so since we have this 2 transition states, you can determine now which is the favorable pathway for the nucleophilic group. In this case, it is the methyl group, okay? It is the methyl group. We want to attack the carbonyl group. We want to attack this carbon. And then, so this is one pathway, okay, coming this way. So what this nucleophilic group will see is that I only need to beat the pathway where I encounter 2 hydrogens, okay, comparing to the other angle that is also 107 degrees. Okay, I'm showing you this angle right here. 107 degrees relative to the carbonyl group. Okay, so pathway A, pathway B. Are you following my hand, everybody?
Yes.
Okay. And on the other transition state, I can have this pathway C or pathway D. Okay, so A and B and C and D. So tell me, William, which is your favorite? Which
for that one, A.
The A, yes, because it is experiencing the least steric hindrance. Am I right? If I approach approach this carbon with the nucleophile this way, I call it pathway B, then the nucleophile will experience more the steric hindrance from phenyl group. This is a bulky group, right? Okay, and so the same with pathway C, okay, bulky group here. And D, pathway D is not as good because this methyl group is bigger compared to this hydrogen alone. Am I right? Okay, so William, you're right. Pathway A is most favored during this transition. Okay, and so the answer will be for you to sketch your product. Newman projection this way, okay? If you are able to do this attack according to William's suggestion, okay, then you will be able to create a alkoxide, okay? When the nucleophile comes in, this double bond will bounce upwards and create a alkoxide. So it is O minus here. And this O minus on the alkoxide will be protonated with, I think in our experiment, it's sulfuric acid. And you, after protonation, you will produce that hydroxy group. So this is the answer, okay? I'm talking about the example I show you in this chapter. I have this handout chapter already published, uploaded on our beach board. Okay, go ahead and download. It is a very short chapter. Okay, and I have more in details in another chapter I published. It's not my publication. Okay, so I uploaded for all of my students. Okay, but this is something published at, I don't remember, it's UCLA or UCI. I don't quite remember. Okay, all right. So look at this. Okay, the other transition state. Okay, with nucleophile coming 107 degrees towards the carbonyl carbon. Okay, experience. I see red dot right here. It is showing you there is a repulsion right there. Okay, more repulsion compared to this direction. Am I right? So for this reason, you are to produce, okay, hydroxy group, and then the new nucleophile, okay, coming to this carbon, and this is going to be the stereochemistry of the newly created chiral center. Okay, keeping the other three from the first chiral center the same. Are you all with me? This is what Felking-Ahn model asks you to do. All you need to know is on the first carbon chiral center, are you able to determine large and medium and small? Okay, then you write it either way, and then you do this 4 pathway of a nucleophilic attack and choose which one is the least repulsion, experiencing the least repulsion. Okay, and it is the steric hindrance you want to consider. Okay, with Felking-Ahn at this stage, this is what you should know. Okay, from this experiment. Are you able to understand, Andrew, since you're doing this the first time?
Yeah, I already did the lab report, so I think I did it right.
Okay. Okay, then next I want to show William. Okay, let me see here. I will show you what I drew. Okay, this is from my pencil. Okay. Oh, is everybody here? Let me see.
Yeah, almost.
Okay, good, very good. All right. All right, so do you have your lab manual opened already? Can you flip to this page? Let me take a look. It is page 38. Okay, I don't want to go back and forth now, okay? I want you to draw this molecule on page 38 according to Felking-Ahn, okay? According to Felking-Ahn, and then you will see phenyl group, okay? You can either go this way or the other way, okay? And you can determine, okay, your pathway of attack, okay? I don't want to show you the, my answer on the screen too long, okay? I'm not supposed to release the answer, okay? Right now, I need to continue with the lecture. Okay, the Felking-Ahn is for you to worry about the largest, the medium size, and then the smallest group on the first chiral center. And I want to move on and talk about the other model you're supposed to learn from this chapter, okay? And let me tell you, in addition to Felking-Ahn, there is another model called Cram Chelation. Okay, all right, so before I open this chapter again, let me go back to the syllabus, okay? page 38 again, okay? Don't forget, you want to learn 2 models, okay? And it is Chelation on, already learned, okay? Cram Chelation model is another one. Okay, if you understand Chelation on, you will be able to understand Cram Chelation easily. Okay, the only additional consideration will be the presence of metal. Okay, in our Grignard reaction, we have a metal, magnesium right here. Okay, and because of this magnesium, it's a Lewis acid. It is also available providing some 2p empty orbitals for the lone pair from oxygen to share in between. Okay, so in other words, transition metals also like magnesium metal, and you will learn zinc, okay, is one example. Titanium, copper, +2 charge, cerium +3 charge, manganese, +2 charge, all capable of doing chelation. Okay, so you learned Chelation on already, okay, but in the presence of metal like magnesium, zinc, and you know, I just mentioned to you the copper plus charge, copper +2, or titanium +4, etc., then you can do chelation. When you have this chelation transition state, then you're able to move the substituents on this first chiral center in a position that facilitating the chelation of metal. Okay, and I'll show you the example right away. So actually, there's 2 models people always learn, okay, you know, side by side. And let me tell you, this Cram, this chemist by the name Cram, Nobel Prize winner, okay? And I remember he won the Nobel Prize when I was a student, when I was a graduate student, okay? He made himself world famous by creating a lot of new molecules, I don't know what is this new carbon new bond. Okay, so look at these 2 molecules. You're doing this Grignard reaction, and the new bond is actually right here between this carbon and the nucleophile. Okay, let me see. This is the carbon we're interested for the new chiral center, and so this is a new carbon bond. Okay, and it so happened that these chemists, they study a lot. They change the substituents on the first carbon, on the second carbon, and they create whole era of new molecules in the world of chemistry, okay? And let me tell you, people even use this Grignard reaction, okay, thanks to the model which are capable of making prediction, okay? And they make a lot of new drugs, new drug molecules, okay, from this type of a reaction, okay? It's just amazing. Okay, nowadays, some hormone or, you know, a lot of UV absorber, for example, these new molecules are all coming from this synthesis, okay, new carbon-carbon bond. Okay, and I think one of the estrogen will come from the Grignard reaction, and these people making the models, okay, become really powerful in designing new molecules. Okay, all right. So I want to share with you right here. Okay, I want you to see our first carbon already have 3 substituents. Okay, and then the second molecules also have a phenyl group, okay, just like a first carbon, okay? And then you notice in this reactant molecule, there is a OH group on the alpha position, am I right? And this molecule with this hydroxy group on the alpha position will not produce sometimes desirable product as what Felking-On will predict. And therefore, Cram Chelation model become quite useful, okay? And let me introduce that right away in this chapter, okay? I'll show you this chapter right away. So when you have alpha hydroxy group, then you will see this chelation from the metal will participate a very important role in the transition state. Okay, now we're talking about transition all the time, because you need to know when the nucleophilic group comes in, what does it mean to this substrate molecule? Okay, with chelation, okay, I want you to look at this molecule I'm talking about. Okay, then we go back to our real experiment, okay? On this first carbon, you have methyl group and methoxy group. If you just go by the Felking-On model and you determine the size of the group, now tell me between methoxy and the methyl group, which one is bigger? Which one has priority?
Methoxy.
The methoxy, it is. Thank you. Who gave me that answer? Mariana?
Yeah.
Mariana, I will give you 1 point, okay?
I think I said it at the same time as someone else, but I don't know who that someone else was.
It was George and Mariana. They said it at the same time.
All right, thank you, George and Mariana. I will give you, yes. Oh, so you're texting now, right? Okay, let me open up the, okay, I want to get you involved, okay? So that I know you're actually registering the message at the same time. Okay, please text me, okay? And let me see, I need to see the ... and see who's chatting with me, okay? Thank you, you get 1 point each, okay? Thank you, and let me move forward, okay? Because when you determine the priority, you know which you want, you just want to compare the first atom connecting to the chiral center, and you know oxygen is bigger than carbon. That's why methoxy has higher priority. Okay, so Felking-On model says, I need to do this 90 degree, right? 90 degree with the largest group, 90 degree to the carbonyl group. And you can draw the other way and you can determine the attack. Okay, no problem. But the thing is, I told you just now, okay, if you have a metal capable of forming chelation, then you want to move this substituent in a position that is gonna be chelation transition state. Okay, so what kind of metals are capable of doing this chelation, please? Okay, magnesium, is this our reaction now? Yes, we're using Grignard region, right? We're using magnesium, am I right? Okay, zinc and copper +2, titanium, and I already said that, manganese and then cerium, okay? These metals, if these metals are being provided in the reaction mixture, then please move your substituents so that the chelation is possible. Okay, this chelation is critical and critical and critical in the determination of favorable pathway of nucleophilic attack, okay? Watch out for this, okay? So, you know, Felking-On says, hey, 90 degrees, the largest 90 degrees, okay? Sorry, because I have metal capable of chelation, then I have to move methyl group up and I have to do the chelation. And then that will change the original, distribution of hydrogens and then the other substituents relative to the one that is attached to the carbonyl group carbon, okay? Okay, then, you know, look at this. This methyl attack, the nucleophilic attack become more readily possible from this angle. Are you following my hand? This is the arrow that it will do the attack because this is the least steric hindrance. All right? Okay. It's providing the least hindrance to the nucleophilic attack. And therefore, this product will be produced in major quantity. Are you with me now? Okay. So I want you to register this message, okay? When you have this metals available to you, please move this substituent, okay? So what kind of substituents will do this? I want you also write down, okay? OR, that means the ether group, okay? Or it contains nitrogen. Where? On the original chiral center. Original chiral center, it comes with a methoxy, okay, or a ether, okay? This is the ether, right? Okay, or tertiary amine, secondary amine, doesn't matter, okay? Nitrogen is also providing the lone pair. Okay, it is the lone pair electrons coming from either oxygen or nitrogen or sulfur, okay, capable of sharing the electrons with the metal, the chelating agent, okay, because these metals must have some empty orbitals for the non-bonding pair or the lone pair to occupy. Okay, chelation is occurring that will determine the orientation of the nucleophilic attack, okay? All right, then you may say, Ms. Jean, okay, is this because, all right, Chem, wait a minute. Cram model, Cram Chelation model, is it coming from nowhere? No, it is not coming from nowhere. It is all coming from the result of a reaction. They conclude this must have happened, okay, making this reaction proceed and produce a product that must have gone through this transition state, okay? So it is not 90 degrees to the biggest group, not anymore. You want to do chelation. This is more important than the 90 degree, okay, largest group. Okay, it is more important to form chelation now when you make the prediction, okay? Okay, so be careful. Alpha hydrogen carrying these three, okay? Either hydroxy or ether, okay? Or tertiary amine, secondary amine, etc., or sulfur group, okay? If you have this three, please write the chelation, all right? All right. You may say, Ms. Jean, sometimes I see other metals provide. Okay. You may see other metals provided to the reaction mixture. What if I see lithium, sodium, potassium, etc.? Then I can tell you because these metals do not form good orbital sharing, okay, with oxygen in this Grignard reaction, okay? You can just follow Felking on, no problem. Okay, it is only these metals showing high tendency of chelation, okay? Okay, so there are restrictions, there are limitations of Felking-Hahn, okay? But there are also restrictions on the Cram Chelation model, as well, okay? Only when you see such groups on the alpha hydrogen, alpha carbon, or if you see metals of this type, you're able to use the Cram model, Cram Chelation model. Are you all with me? Are you all with me? Hello?
Yes.
Okay. So I think, William, once you have this model, okay, one more model in place, you will be able to make better prediction, okay? You will be able to make better prediction. And I can tell you, the answer is 2A, okay? On the lab manual right here,
Mm-hmm.
okay, it is 2A,
Okay.
form in majority, okay? And I want you to do a little bit more exercise, ladies and gentlemen, okay? And we'll see, okay, in the final exam, you probably will see questions like this, okay? I give you a molecule, please draw the transition state and determine, okay, the molecule that will be formed in much preferred pathway. And sometimes the question may ask you this way, okay? I give you a reaction like this, and I produce a product like XYZ. Now tell me, is this molecule XYZ following the Felkin-On model, or it is following the Cram Chelation model? Oh yeah, we can also challenge you this way, okay? So you need to understand how to draw the transition state in both model. Are you with me? Okay, and now you know the whole trick is with Cram Chelation, you just have to move the substituents on the alpha carbon, okay? Move the transition so that chelation is possible, okay? Okay, so let me show you. This is my drawing, okay? I shouldn't be publishing this at all, but I don't mind showing you, you know, my first part of the drawing. Okay. Take a look at this, because we have Grignard region and magnesium is capable of doing this chelation, okay? And so from the first spiral center, I have phenyl group, and then hydroxy group, and then hydrogen. Okay, so with this chelation, I'm able to show you nucleophilic attack is much preferred this way compared to the other way. Okay? And then after protonation by sulfuric acid, you will be able to turn alkoxide into alcohol. Okay? And so this is what you need to watch out for. Okay? Now, and students were saying, Miss Jean, can we sit back a little bit now? Where do you get this alkoxide here and the alkoxide? Okay, then you probably remember what I told you about this mechanism, okay? And let me go back to the syllabus right here, okay? Okay. Are you ready to go now? Everybody, are you ready to go?
Yeah. Hello. Yes.
Yes.
Good. Okay. All right. Grignard reaction attacking this molecule. And look at the end result. This hydroxy group. It seemed unchanged, okay? But actually, I can tell you all hydroxy group is sensitive to Grignard reagent. Okay? And I want you to know that in this reaction, you actually need 2 moles. Are you with me? This is a key point, okay? For each molecule of the benzoin, okay, you will need 2 moles of Grignard reagent. Okay, can someone tell me, how do you make this Grignard reagent? How did you do it?
Like the actual steps or?
Yes, experimentally.
Okay. We added 290 milligrams of magnesium, and then we did a stir,
Mhm.
a small stir with the stir bar, and a 100 milliliter round bottom flask.
No, don't read the procedure to me. What are the key reagents involved in this Grignard reagent production?
Oh, I see what you're saying. The magnesium, diethyl ether, and
Solvent, yeah.
yeah, and then the MEI, the
Okay,
methyl iodide.
methyl iodide. So in the presence of ether and hydrous ether, magnesium will dissolve into halide, methyl iodide in this case, okay?
Mm-hmm.
I tell you, the quantity we write in the procedure is not coming from nowhere, okay? We actually did the calculation. You need 2 moles, and we actually add whole magnesium in large and very large excess, large quantity, okay? And you need 2 moles for each mole of benzoin provided. It is because you need to take care of this hydroxy. In addition to this nucleophilic attack that will require 1 mole. The other mole of the Grignard reagent is to take care of this hydroxy group, okay?
Oh, so having simultaneously. Okay.
Okay, now tell me, now students who participate Tuesday lecture, can you tell me, when you attack the hydroxy with Grignard reagent, you will be producing a gas. What is that gas?
Methane?
Methane, yeah.
It's methane, yes, okay. And did I tell you there is a typo right here? Okay.
Yeah, this ethane.
Okay, the M is missing, okay? It's methane gas, okay? All right, now ladies and gentlemen, it means this hydrogen is already gone, bubble away. It bubbles away. The methane gas, it forms CH3 and the hydrogen here together forms methane gas. And this methane gas bubble away. Am I right?
Mm-hmm.
So what happened to this hydroxy now? What do you write?
What?
What do you write here? Instead of OH, what do you write at the end?
It's just a
O
O, like a
minus.
negative.
O minus.
O
Yeah.
minus? O minus, but you know, your methane is already gone, right?
Yeah.
So what is the counter ion of this O minus?
The magnesium.
Alone?
The magnesium. Like the MgI.
MgI. It is
Yeah.
magnesium iodide with, what is the charge right now? It is going to be +1 charge, okay? Am I right?
Mm-hmm.
Thank you very much, Andrew. I want to give you 1 point. It's not easy to see that part, okay? Young students usually don't see this, okay? Okay, everybody, every chemist knows, okay, hydroxy group is potentially releasing hydrogen plus to Grignard reagent, okay? So when you see bubbling, you know the Grignard reagent is actually attacking something on your reactant molecule and producing some side product already, okay? So I told my students all the time, running this reaction is super, super dangerous. Number one, you're using the ether, the anhydrous ether as a solvent. Remember that? Okay.
Yeah.
Is ether very flammable?
Yep.
Yes. Is it very volatile?
Yep.
Yes. Okay. I can tell you when students run this reaction, I usually want everybody identify where the fire extinguisher is. Right before you start the reaction, any Grignard reaction, okay? It doesn't matter which substituents, which reactant we're doing, okay? We want to control the fire hazard, okay? And on top of the ether, that is super dangerous, very volatile. Boiling point of 37 or 36 degrees is actually your body temperature. You hold ether in your hand and it boils away. It forms bubble. It's just like bubbling, water, boiling water on your cooktop. Very scary, okay? Evaporates so quickly when you hold in your hand long enough, okay? And at the same time, you're producing the CH4. Am I right? Is it super dangerous? Yes. So on top of the ether, you have methane gas. And so let me tell you, it is like double the devils, okay? Double the devils in this reaction. Okay, you have two flammables in your reaction mixture. Are you all here? Are you all hearing me? Okay, it's very scary, okay? All right.
I just want to add that I'm excited that we're not in lab for this one. Okay, cool.
Okay, you're well, I say it's lucky and unlucky. Okay, once you run the Grignard reaction, you realize, hey, there's not much more. If you're able to survive this reaction, you should be able to survive other reactions without major problems. Okay. This is a very dangerous one. So for this reason, we only run this reaction in small quantity, everybody, okay? And so let me tell you, this hydrogen is gone. The minute they meet each other, Grignard reagent and the benzoin, the minute they meet each other, the hydrogen is gone, okay? So you have magnesium iodide attached to this oxide right here. Agree?
Yep.
You agree? Okay. And on top of that, hello, you want to see this reagent, the Grignard reagent, perform a nucleophilic attack onto this carbon. Are you following my hand? Okay. So tell me, how many moles of magnesium do you want? 1 mole for the Grignard reagent to take care of the OH group. The other mole is to take care of this nucleophilic attack. Are you all with me?
Mm-hmm.
Okay. Is this common sense? Yes, it's common sense to chemists. Okay. Just because normal reagent, Grignard reagent for normal reactant without hydroxy, yes, I only need 1 mole. But thanks to this hydroxy group, I know I need to take care of this hydroxy group, and it's producing a very, very hazardous methane gas. Okay?
I have a question.
Yeah.
So in my reaction mechanism, I did not draw plus CH4 because it's not in the main root. So
The CH4 will be produced.
no, I know, but I'm saying I didn't draw it in my mechanism because it's like, where do you put it?
Where do you put it?
Yeah. Is it just an assumed thing that you know that it's going to go away as gas? Like,
it's actually 2-step, okay? You can show me the first step is for this Grignard reagent attacking OH. Then you can show me the second step. This is attacking the carbonyl carbon.
Okay,
Okay.
I don't think you're yeah,
There are,
I
there are two reactions here, in other words.
no, I know. I drew them both. Like
Good, good,
I
good.
but
You
that's
need
not the
to,
problem. The problem is where does the CH4 go? Like
the
where do you
minute,
put it?
the minute they come together, the Grignard region and the OH group come together, the minute the CH4 will be produced.
No, I know. And it goes away as a gas, but in your mechanism,
I
where
think
do you
he
put
means,
it?
I think he means like how to write it. Like how would we write it in our mechanism?
Okay,
Right.
I think I did it last time and you were not here, okay? Here. You
Okay, yeah. That's what I'm saying. Okay, never mind. You'll see. I'll just turn in a lab report. You'll see. Because
Okay,
like I, uh, it's just not in the main route. So I didn't, never mind. You'll see what I'm saying.
good, good. Okay. You're saying, hey, this is not the classic nucleophilic attack we're talking about. Yeah, I agree with you, okay? And I want you to show me before you even do the nucleophilic attack, this is already doomed, okay? Okay?
Yeah.
It's a common sense to all chemists in the world, okay? All right. Okay, and let me keep going. Okay, so do you understand you need 2 moles of Grignard reagent, okay? And so when people write 1 and 2, like 2 different steps on top of the arrow and below, it means this is for the reaction producing the main product, and then this is the one for the workup, okay? Okay, and I want all of you to remember, once you produce the alkoxide, okay, the counter ion is magnesium and the iodide, okay, and then you do the nucleophilic attack, you produce another alkoxide, and this is the minus charge. Am I right? Am I right? So if I ask you how many moles of alkoxide can be produced from this reactant, can you answer my question? How many moles of alkoxide is produced when you introduce the Grignard reagent? Tell me.
2.
Who says 2?
George.
Thank you, George. I will give you 1 more point. Very good. You're right. It will be 2 moles of alkoxide. Okay, 2 moles of alkoxide. And they are all waiting for protonation later in order for you to produce this hydroxy group and hydroxy group. You are making alcohol, okay?
Yes.
You're making, yes, this is a secondary alcohol and this is a tertiary alcohol. Am I right? Okay, thank you, George. You get another point, okay? All right. And what do I want to tell you about this reaction before we step into this workup? I want to also share with you, okay, right here. We talk about this chelation, okay? Imagine in your own reaction molecule, it will be oxygen and then magnesium and then iodide here, okay? And the other one is gonna be magnesium, okay? And then iodide also here, okay? This is not the best not the best way to present the transition state. In fact, okay, I mean, I'm not gonna talk about too. Hey. Love it. Yeah, relax a little bit. Okay, you know this is alkoxide, okay? Potentially with another like magnesium here, iodide here, okay? And here, carbonyl group, once you do the nucleophilic attack, there is another magnesium coming here. Am I right? Okay, and all because oxygen can provide lone pairs, 2 lone pairs from the carbonyl group and 2 lone pairs coming from your originally hydroxy group. Okay, so those lone pairs are very effective forming the chelation, and we call this, if I use zinc here, yes, it will serve the same purpose as magnesium. It is Lewis acid. Okay, have you learned this term, Lewis acid? Okay, magnesium iodide is a Lewis acid to activate this carbonyl group. Okay, do not ignore the significance with these two arrows here. It's a very important arrow, okay? Why do I want to tell you this? Okay, because when I learn chemistry, I have to make myself convinced. I fully agree with what the inventor was saying, okay? It makes sense after, learning chemistry a couple years. It makes sense.
Intermediate stuff.
It makes sense, because I have metal right here, and metal has empty p orbitals, okay, taking the lone pairs away. So what does it mean to this double bond right here? It shows the trend, am I right? Okay, the carbon carbonyl group right here. Oxygen is more electron withdrawing compared to carbon. And therefore this double bond right here, it's not even in the electron distribution. Do you agree? It's more concentrated, the electrons more concentrated near the oxygen. Do you agree? So we always write partially positive here, and then we always write partially positive here with this carbon. Am I right? Yes. And normally, yes, we have this electron distribution already uneven. Now with this arrow right here, hey, you notice this lone pair will be sucked away with the empty p orbitals or d orbitals in this transition metal. Guess what? The electron distribution will be even more uneven compared to the regular carbonyl group. It's more partially positive than before now on the center carbon. This carbon right here is more partially positive, more positive than before. Do you agree with me? Okay, because of chelation, you activate the double bond. You activate the carbonyl group. You make this carbon even more electron hungry than before. This is why the nucleophilic attack can just go in without any problem. Okay? Okay, so what is if you ask me, what is the function of magnesium here? It is not just chelation, okay? Stabilize the transition state. Okay, so the metal has two roles here. It stabilizes the transition state, okay? Number two, activates the carbonyl group because the electron distribution is even more toward the oxygen side. Okay, and every chemist agree with what I just told you. I learned from them, and I'm telling you, this is what chemists believe. Okay, so adding this chelating transition metal stabilize the transition state. It makes this carbonyl group even more active than before because now this carbon is more electron hungry than before. Okay. Okay. And so I think I am pretty much done, okay, with this Cram Chelation model, okay. Let me talk a little bit about our experiments. How about that? Are you ready?
Yep. Yep.
Okay. One more time. How many moles of alkoxide is formed during the nucleophilic attack? There are two of them. Yes, thank you. George offered the answer. Okay, there will be 2 alkoxide, one from here, one from the carbonyl group, okay? And then what do you do in the reaction? When you do the workup, okay? Let me talk about a little bit on the procedures. Let me see who's here now. I have 8 students. Okay. Okay, you dissolved magnesium into the halide and you stir. And I told you this is super, super dangerous, okay? And let me tell you, during the generation of Grignard reagent, let me ask you this. Now, this is another common sense. Do you think this reaction is exothermic or endothermic?
It's exothermic.
Exothermic?
I remember in 320L, you guys ran a Grignard reagent reaction, am I right?
Mm-hmm.
Okay. I don't know whether your lab instructors asked you to, you know, prepare for a ice bucket and you want the ice bucket standby. Okay? Because oftentimes, you know, the reaction itself during this process, during the preparation of, hey, right here, preparation of methyl magnesium iodide, this is the Grignard reagent, okay? It generates heat, and that heat actually evaporates some of the ether, okay? And when that happens, my goodness, the reaction mixture turned really, really pasty because you're now losing the solvent, okay? It is just like, yeah, you're making soup and then all the water evaporates when you're making the soup. Then the soup tastes really, I wouldn't say taste, will look very pasty, am I right?
Yes.
Okay, if it is pasty, it actually dissipates the heat poorly. That means there will be some hot spots here and there in the paste. It's more difficult to stir the soup. And you realize your magnetic bar will not turn anymore. Is this good news or bad news? I can tell you there will be a lot of side reaction. Yeah.
Bad news.
So for this reason, you always need to contain the anhydrous ether in place. So we install a condenser on top of the Chelation adapter, okay? You know, when you write the pre-lab procedures, okay, I don't know if you have this habit of doing this apparatus drawing. I always do. Okay, and I can actually take more precautions when I run the reaction. If you see the glassware, okay, and you have a condenser. Do we need a condenser here? We have a reflux condenser, am I right?
Yeah.
That condenser is super critical, okay? So in case of any ether escape from the reaction, make sure you want to condense it down with cold water running at all time. And actually, during the generation of Grignard reagent, you also want ice, okay? Because oftentimes you see this condenser, boy, ether evaporate and condense, oh my goodness, that reflux is so vigorous, and then you see this, the solvent amount reduce over time. Okay, if that happens, you just have to add more solvent from the side arm of the adapter. we use the Chelation adapter right here, the Chelation head adapter. Okay, it is actually 2 arm. Okay, one arm is connected to addition funnel. It looks just like a separatory funnel, but it comes with the joints, so it can be sealed, okay, along with your adapter. So that addition funnel connects to Chelation head adapter, and then the other arm of the adapter will be mounted with the condenser, okay? And this is quite, I think you run 320L before. It is not a surprise. It is for you to control the amount of ether at all time. Okay, and don't forget you're generating methane gas at the same time. So this methane gas evaporation also can bring some of the ether out. So, you know, watching the viscosity of the reaction mixture is, it's very critical, okay? It's very important in terms of controlling the generation of Grignard reagent. This part, I have to say, whoever invented this, okay, the Grignard, the French scientist is the name, okay? The Grignard is definitely a genius when he ran this reaction, okay? He must have blew up quite a few reaction mixture to learn the whole thing, okay? It's, you know, a lot of the chemical reactions just risk-taking, okay? All right, so you're supposed to add the methyl iodide into the ether solution that already has the magnesium, okay, dispersed in it. You only introduce the halide dropwise, okay? This is also critical. Okay, now tell me, what is the purpose? Why you have to add this dropwise? Because you want to control the exotherm, am I right?
Yeah.
Okay, you want to control the exotherm. You don't want the heat generated in, oh, yeah, yes, in 5 minutes, all at the same time. I can tell you, yeah, any chemist, yeah, will know, yeah, control exotherm, having ice bath standing by, yeah, is critical to a Grignard reagent, okay? All right, at the end, okay, you produce the Grignard reagent and you want to make sure most of the magnesium had reacted. How do you know? Ladies and gentlemen, how do you know most of the magnesium had reacted?
There'd be a color indication, first of all. And second of all, there would be like the temperature will come down and the reaction will slow down.
How do you know reactions slow down then?
Through one of the chemical processes, like either a color change indicator or the exothermic, like it would the heat would be reduced, which means there's less exothermic activity.
Also say that you don't see as much gas production.
Yeah.
That's a good indication. If the CH4, yeah, methane gas is reduced. But the thing is, the ether also bubbling away at the same time. So both molecules contribute to foaming. Foaming means bubbling. So you cannot really tell. Unless all the ether is gone, then you don't see any bubbling. Understand? We want you to pay attention to how do you know magnesium, most of the magnesium had reacted. You both over-engineered, okay, young lady, gentlemen. How do you know most of the magnesium had reacted?
Will you not be able to see as much of the magnesium spurs in the solution?
You're right, William. You made a very good point right there. Because you add so much magnesium solid. Am I right? And then at the end, there's not much solid of magnesium floating around. This is a true indication, okay? Because all the time you see ether bubbling away. You see when ether is bubbling away, okay, it is boiling. It is producing a lot of ether vapor. As long as you have a solvent there, this is nonstop, understand? Okay? So I can tell you, only when you add a lot of ice, control the exotherm, okay, the bubbling will completely stop, okay? But this is not the ideal temperature for the Grignard reagent, okay? You still want some temperature there for the reaction to kick off, okay? You don't want to terminate the reaction, understand? So it is very, very subtle. I can tell you, running this reaction, I never fail in my whole life, okay? And as long as you can control the moisture, okay, as long as you know what to watch out for when you generate the Grignard reagent, okay, you have this cloudy gray white paste, okay, that is supposed to be, okay, the Grignard reagent should have that appearance. It's just like a cloudy gray, it's ugly yogurt color, okay? And right here,
Grayish green color.
yeah, it could be a little bit greenish, you're right. And then let me tell you, you're using heating mental voltage regulator. Oh, I can tell you, I never want heat, okay? It is just crazy. I don't want heat when I run the Grignard reaction. I've seen people, you know, make boo-boo turning on the heat, okay? You don't need it. Okay, you want to allow room temperature, okay, occasionally with some ice bath, okay, cooling down the reaction temperature from outside of the reaction flask. That's it, okay? That's all you need, okay? All right, so I think I've done enough here, okay? I think the key point is the reflux. And you know, if we were to run the reaction, I will tell you, inside of the condenser, if you see the reflux ring, which generates drops of either solvent from the condenser, okay, it evaporates and condenses and produces droplets. You want that droplets roughly one drop per second. It's called good reflux, okay? And this is what I want students to watch out for, okay? All right, anything else? You may say, Ms. Jean, what if the reflux gave me the droplets of ether, like 2 drops per second? If you encounter that situation, what would you do?
Please ask the question again.
Reduce the heat.
Well, you're not heating. So what do? George? How do you control the reflux rate?
Oh, on what you're adding. You like slow.
Okay, you stop adding the reactant. What else? The best way.
Can you
You can cool down the entire flask by adding it to an ice bath.
Thank you. Okay, all you need is throw some ice. Okay, thank you, Andrew. Very good.
You just
Okay.
gotta be careful not to cool it too fast, because then,
Yeah. Yes, this is what I do to help my students. If you throw some ice, okay, to quench the reaction mixture externally, okay, in other words, you want this ice bath, a large beaker, okay, and then your the reaction flask, the round bottom flask, sit inside a big beaker. And this is empty space to begin with. But if you see reflux is out of control, if you see the bubbling is actually producing a lot of ether droplets on the condenser, all you need to do is throw the ice into the beaker. Understand? And then right after that, hey, when the exotherm is under control, take the ice out. Take the ice out because you still want the room temperature to facilitate the reaction to continue. Are you with me? Okay.
Yeah.
So yeah, this is all common sense. And although we don't run it, I still want you to, pay attention. There's actually a lot of hands-on skill associated with this paragraph, okay? This is a critical stage. If you cannot produce a Grignard reagent successfully, the second step, synthesis, this is just impossible, okay? If you see weird exotherm, okay, or if you see some weird precipitate coming from this reaction, that means you already have side reaction, okay? And this is too much for you to imagine yourself. I am experienced enough to tell you, just by looking at your reaction mixture, I will tell you whether you made it or not, okay? So this is requiring some hands-on, but we don't have the luxury to do it with our own hands. Let's do the second part, okay? All right, you have your Grignard reagent already made, and now you want to introduce your reactant slowly by adding, they want to add the methylene chloride first, okay? Okay, and then the reactant is introduced. Hey, how come? Okay, we're giving you plus minus sign. That means this is already optical active, okay? And this -1 right here, it means this guy, reactant, okay?
Mm-hmm.
Okay, that reactant, okay, pre-dissolve, okay, what is the purpose? I want to introduce that in the diluted form. What is the point? You want to control the exotherm, okay? Now, I want to invite everybody to tell me, why is this step producing heat again? If I want to introduce in the dilute form, that means I want to control the reaction heat drop by drop in diluted form. So where is the heat from?
From the nucleophilic character with the, like from the electrophilic carbon in the carbonyl group. The formation of the carbon-carbon bond.
Excellent answer, Andrew. Andrew gave me a very good answer right here. I give you another point. So Andrew, you got 3 points already today, okay? I want all of you to take a look. This methyl group right here is coming from your Grignard reagent. This is your nucleophile, okay? And then this carbon right here from the carbonyl group, you're forming a new bond here. And tell me, new bond, carbon-carbon bond form, this new bond is formed. Is bond forming reaction exothermic or endothermic? It's exothermic. Thank you. Okay. Yes. Forming new bond is exothermic. It is exothermic. Okay. For this reason, I want to dilute it, or else you're turning the reaction into a bomb again. Okay. Don't forget, you have a lot of ether. Okay. When the bomb. When the bomb is created in front of your eyes, it's really no fun, okay? And we select this methylene chloride as a solvent because this is fire retardant, actually. Okay, any halogen containing, a solvent, it is fire retardant. Understand the word retardant? That means it does not catch fire, okay? Halogens, especially bromine, is used in industry as a fire retardant quite often, okay? All right, next. Okay, oh, we told you it's not gonna be methane, it's ethane. It's not gonna be ethane, it is methane, right? Okay, you will see that, okay? Then, the addition is complete. Hey, I'm gonna do a dropwise, okay, and ice water ready, okay. Then reflux, okay. And this is assuming, okay, because we already add the flame retardant. Yeah, I don't mind reflux a little bit by heating, okay, to speed up the reaction. And then check the TLC by spotting the reaction mixture onto a TLC plate. Aha. What do we want to do that for? Tell me. I can
So
tell
we
you.
can track the reaction.
Oh, someone is talking. I mean, besides Andrew, who is it?
Oh, it was, I'm thinking
Mariana?
to check if there's still gonna be some of the benzoin on it.
Thank you. Keep going, Mariana. Keep going. So what are you supposed to see?
The dots, the 2 dots, I think it will show.
Is it 2 dots or 3 dots?
Well, it might be 3 because then we'll keep on recrystallizing, right, to get rid of the benzoin.
Young lady, how many products are you making?
The 2 dots.
Yes, it's probably 2 dots, okay? And you want to run it against what? TLC? What is the reference dot? What is your reference dot? What is a good reference dot? Do you understand reference?
Yeah.
Something that you know about the structure and you know the compound for sure. Hey, look at this. What is a good reference here?
The benzoin and the
Thank you.
methyl.
Okay, let me tell you. Yeah.
Either.
Yeah, students will be able to find benzoin and then product, and potentially, because I'm making two products, one of them is in major quantity and the other one, yeah, okay. And maybe I'm able to see some, I don't know, okay. So I'll say 2 to 4 dots, how about that, okay? 2, minimum of 2, and 3 because I may have some undesirable, okay? And 4 because of this, okay? Make sense? Okay? All right, so running TLC, very good, Mariana. I'll give you 1 point, okay? You know, tell you what, I know a lot of you have great potential and probably you didn't do very good job making a good report or, you know, answering the in-class questions. So I'm trying to make up some points for you, okay? The TLC plate. Okay, and then, you know, I did ask my student to run it, okay? Last year, we were very, okay, so some benzoin already pre-spotted. Look at that. This is my reference, okay? Okay. Further heating may be required depending on whether you are able to finish all the benzoin, okay? Okay, so your product mixture, as long as the benzoin disappear, go ahead. You can turn off the heat, okay? Or stop the reaction. So how do you stop the reaction? Besides turning off the heat, what is the right way to stop the reaction? You actually slowly treated this reaction mixture with 10% sulfuric acid, and it is 50 ml. Stir for 1 to 2 minutes. Now tell me, can someone tell me what is the purpose?
What is the purpose of what?
Adding the sulfuric acid.
So put the hydrogens back on the O minuses.
Ah, you're right, you William. Thank you, okay. Thank you very much. You're right. You're protonating the alkoxide, we call. Am I right? Okay. Now, attention, everybody. Okay. I'm not going to go any further because that will involve in your flowchart writing, okay? But I guarantee I will check why 10% sulfuric acid and 50 ml. Can you figure out the moles right here? I guarantee I will check this number. What is the moles of sulfuric acid here? What is the moles of hydrogen plus here?
Like, do you want us to say it?
Wait.
One more time. When I grade your pre-lab, I want you to tell me how many moles of sulfuric acid you'll be adding and how many moles of hydrogen plus you're adding.
You want me to say it right now,
No,
or
no. You will have to show me in the pre-lab writing.
okay?
This is the moles I want you to check. This is not a quantity we provide to students just for fun, okay? This is all through calculation.
Mhm.
Okay, so we give you 50 ml. Is this sufficient? Okay, and the rest of it, I want you to handle the flow chart yourself, okay?
Yeah.
Okay, now this is not the end of it. I need to continue procedures. Okay, now because this is flow chart writing, I want you to figure out, okay? Yeah, you know, the point of education is to maximize students' effort, okay?
Yeah. Hold on real quick.
Can I give William another point for saying protonation of alkoxide? Thank you. Okay, so Mariana, George, Andrew, and William, you all contribute good answers today, okay? Very, very good. I encourage you to do so. It means that you really have great potential, okay? And I want to give you, my praise, okay? All right, are you ready for the remaining part of purification? I would call the workup. You want to recrystallize the crude and use this 5 ml and some petroleum ether, okay? This petroleum ether is actually not ether, okay? Some genius named this liquid petroleum ether, but it's not coming from ether. It's nothing to do with ether structure-wise. The chemical composition is not showing the COC. There's no carbon, oxygen, carbon bond. No. It is only hydrocarbon, okay? But it is random length in the hydrocarbon. So we give you a range of boiling point. Okay, so this is a mixture. Are you all with me? Okay. All right. So for every 100 milligrams of the crude, okay. Oh, by the way, how does the crude look like? Are you able to get solid from this process? Yes, you will be, okay?
Yeah. It should be like needle, white needle, like.
That's at the end, Andrew. Before purification is not white needle, okay?
Oh, it should be like
That look like an
before
oil.
purification. It's like a plaster looking type thing.
You're right.
Yellow.
Yeah, it's just a blob of white stuff, okay? White powder. Okay. And I want to put you on test now, okay? Okay, it looks so simple. It is one, like couple sentences here, but people are really, really busting their tail getting that purified product. And it is one lab period, full period, getting that pure product. And so that's why I want to go through it, okay? For every 20, okay, for every what? For every, no, we don't want to give you the amount. We just want to tell you roughly 5 ml at a time, okay? Of what? 5 ml of this high boiling petroleum ether, and I told you this is hydrocarbon only, okay? Different, it's a mixture of many different lengths of carbon bond, of carbon chain, backbone, okay?
Should we put that in the reagent table?
You can put that in the reagent table, and this is only amount you need to list, okay? And I can tell you, I want you to build that habit, okay? I realize a lot of you, in the future, someone will give you a procedure, a protocol, okay? That's its procedure. And then they want you to run the test and just experience the reaction. Okay, this is from your supervisor, you run that reaction. You want to list every single reagent on the reagent table in order to look up the hazard, okay? Are they asking you to run a reaction involving radioactive elements? Or is this involve carcinogen? Or this is very, very irritating to the lung or to the windpipe respiratory system in the human body? You have to know it, okay? Yes, petroleum ether, okay, it's hydrocarbon, and all you have to do is look up, okay, is this hazardous, okay? And I can tell you it's flammable, okay? Okay, just like you go to the gasoline station. This is another hydrocarbon mixture, okay? All right, and so I want you to do this, okay? And tell me, for each recrystallization, okay, so when we say recrystallization, we're trying to purify the solid, am I right? Okay, and we say for the modular core was decanted away from any undissolved solid. Huh. Okay, so what does it mean? A lot of students ask me, Miss Jean, what's going on here? For each recrystallization, you're supposed to pour something out of the flask. All right. All right, bonus point question. What is modular core? This is common sense, okay? This is not 420 level. What is modular core?
The solution that everything is in.
The solution that everything is in? Andrew, think a little bit further. You're on the right track, okay? But we are pouring something out of any undissolved solid. We're pouring something out from any undissolved solid. So we are not asking you to purify that solid by making all the solid dissolve in the classic conventional procedures. Remember, yeah, for recrystallization, you normally dissolve all the solid in the flask completely, remember? But you don't do that here.
So ethanol.
What ethanol?
Right.
We're not using ethanol here, hello?
I mean, ether.
Petroleum ether, hello? Okay?
Yeah,
We're
because it's supposed to be like the non-limiting reactant. Like it's.
Hey, wait a minute. Wait a minute. Is this a reactant? Petroleum ether, is this a reactant?
No.
So what is it?
It's
Is it a liquid?
what do you call it? Solution?
This is solvent, all right? You're
Yeah.
dissolving your crude product, and your crude product, I just asked you, how does your crude product look like? You said, oh, it should be a solid. Yeah, it is a solid, okay?
Mm-hmm.
If you check this, you have such solids mixed together, okay? A melting point like this, melting point like this, two isomers here. So are they solid? Yeah, they are solid, right? So you have solids mixed together and maybe some benzoin still there, but who cares, okay? Right now, I just want to purify the big mess, okay? And I choose a solvent, which is hydrocarbon only. Petroleum ether is only hydrocarbon, okay? It's just different blends in the hydrocarbon chain, I told you, okay? And you want to add the solvent, like 5 ml, okay, but no more than 25, okay? We're asking you not try so hard and dissolve with a large amount of solvent, and then you kill the yield right there. A lot of if you have a low yield, your pure product may not precipitate at all if you add too much solvent, right? This is common sense when you recrystallize something, right? So I want you to read this procedure because a lot of students come back to me during the experiment. For each recrystallization, the mother liquor was decanted away from the undissolved solid. What does it mean? You're reading the English, and it's not even my primary language.
From the undissolved solvent, the
You're
mother liquor was
adding,
decanted away from.
you're adding the petroleum ether to the solid, which is a mixture, a mixture of 2 solids or 3 solids together. Am I right?
Yeah.
Yes.
And for each recrystallization, for each time you purify it, the mother liquor, meaning this is the solution on top, sitting on top of the undissolved solid. The mother liquor is the solution already created when you dissolve the crude product and the petroleum ether together.
So it's the filtrate product.
No, don't go too far. I just want to put the solvent into a pile of crude product, crude solid, okay? And when I dissolve it, I swirl it, okay? I may heat a little bit, and then I said I want the mother liquor decanted away from any undissolved solid. That means I don't want to dissolve the solid completely, okay? I don't want to do it in one shot. I want to do it gradually, okay?
So that means the mother liquid. I just want to make sure I'm right. So the mother liquor has the product inside of it.
Well, this is my next question, okay? All right, now do me a favor, every student. Do you have a piece of paper next to you?
Yeah.
Okay.
Yes.
Then you draw a round bottom flask. Can you do that? Okay. Then pretend you have some solid already sitting at the bottom. And then you add petroleum ether, and then you swirl. Swirl, swirl, swirl. Then you will be able to dissolve the crude product to some extent. Am I right? Okay. So what is the mother liquor? This is the liquid. This is the liquid sitting on top of the undissolved solid, because I know I don't want to dissolve all the solid in one shot. Are you all with me? And the mother liquor is the solution sitting on top of the solid now. That's called mother liquor. Are you with me?
Yeah.
Yes.
Okay.
So is it wrong?
No. Don't go too far. I want to ask you this question now. Is mother liquor supposed to be a saturated solution or not?
Yes.
Yes.
Yes, it will be saturated solution, because when I swirl it, the solid will dissolve, and then I create a solution at room temperature, or maybe I can heat it a little bit. But anytime I dissolve it, that mother liqueur is always the saturated solution if I stir enough, all right? Am I right?
Yeah.
Now tell me, in this mother liqueur, what do you have?
You
This
have the
is
filter
solvent.
product.
What do you have? What do you have in here?
The two
The
products.
Two products. Very good. It is this two products. Okay? And I already told you 2A should be formed in majority. Then in the mother liqueur, what do you expect in the distribution of the 3, 1, 2, and 3? Compound 1 and product 2A and product 2B. Which one should be in majority? In that mother liqueur, which one should be in
2A.
majority? It should be 2A, right? Very
Yes.
good. All right. So when I cool it down, which compound should precipitate then?
2A.
Hey.
Thank you. So we are doing this decanting the mother liqueur in order to do some purification, well, in order to isolate 2A by cooling down the solution. Am I right? Okay, now here am I. Yeah, recrystallize the crude, and then, okay, for each, okay, you want to pour the saturated solution out. And so what do you do with the undissolved solid? You continue adding petroleum ether, and then you dissolve. Then you can pour the mother liqueur out again. I can tell you, this is what industry will do in practice, okay? This is in practical world. They create the saturated solution portion by portion, okay? This is better than trying to dissolve everything. My goodness, I can tell you a lot of times the impurity molecule don't even want to dissolve. And by the time you dissolve all the solid, you already blew up the dilution out of proportion. You cannot collect any pure substance anymore because the concentration is too low when you overshoot the solvent amount. Are you all with me?
Yes.
Okay, so this is the industrial trick. We are just asking you to do the same in the lab, okay? All right, so for each recrystallization, mother liqueur, which is the saturated solution, will be decanted away from the solid, and then you continue into this undissolved solid. After pouring out the solution, you continue adding more petroleum ether, and then you can create another mother liqueur, and you can combine them. Are you all with me? Okay.
Yes.
Then you can collect your purified product. Okay, in white needle. It is beautiful. I even took the photo. Yeah, it's somewhere in my camera, in my iPhone. Okay, it's beautiful. Okay, it is like white needle. Okay, and the 2A dominate. Okay, okay. So I think for today you're able to write your pre-lab. Okay, try to understand when you write the pre-lab. There's actually a lot of tricky things here and there, okay? It looks simple when you write it, but when you deliver the result, you realize, oh my goodness, why so tricky, okay? So far, so good?
Yes.
Everybody? Let me ask you this. Are you able to enjoy experiment in such a dry lab format?
No.
I'm learning a lot more.
Like,
Really? William, are you serious?
Well, I'm learning a lot of like the like mechanisms and stuff much better.
Oh, you know, it's just because I have more time lecturing, right?
Yeah, but I would have liked to be able to do this stuff in the lab.
Uh,
So do I.
Honestly, I would love to do this in the lab with the exception of this experiment because at Cerritos College, there's this kid that was next to me and he was doing this experiment and somehow he closed his system. He turned it into a closed system and the round bottom flask bust open. Yeah,
Oh my god.
and we were sharing the same film hood, so you can imagine my frustration. I was pissed. Yeah. No, I was pissed and then I asked him if he was okay, but initially I was pissed. So, yeah.
You know, have you noticed, Andrew, it doesn't matter, you know, what instructor is trying to show or demonstrate or educate, lecture, etc. For some people, they don't care. They don't care about learning. And I can tell you, it's really difficult to teach the lab in the sense that people are just, you see, some people are just naturally built to do reaction and some people are just not. They're not born with that capability, okay? And they want to make mistake and then be alerted, just like on the computer, okay? Oh, when you click this, it doesn't work and it show you a sign. And you give you a warning right there. Oh, because your password does not match, so it won't go through. Okay, they want to learn that way. But the thing is, in chemistry, especially in the lab, you cannot afford to make mistake that way. Okay, and so we gave you a lot of information. Hey, be careful with this, be careful with that. And it really depends on whether the person's mind is here in place with you. And oftentimes I can tell you a lot of experiments are really super, super dangerous. And this is one of it. This is one of the very, very dangerous one, okay? Running Grignard, I think with 12 students in the lab, it's already maximum. And I heard in one of the city college, someone told me, the instructor was running the Grignard reaction with 30 or 40 or 60 students in the same lab. I don't know. I don't know about that. Okay, 60 bombs. Oh, it's not easy. Okay, so I want you to learn to at least try to understand. We didn't have a chance to run it, and why is this reaction safe until the end of semester? You run it after you finish all the training in the early semesters, because this is the most dangerous one. Understand?
Yeah.
Mhm.
So we save it until the last. when you learn to be careful. Yeah. Okay. So you know something? I noticed. Oh my goodness, Mariana, George, Andrew, William. Thank you for responding to my questions. And you all have great, great potential, okay? And I did reward you with extra credits, okay?
Oh, yeah.
Yes, you will get it. And I will tell Dr. Lopez at the end of the semester, okay? Great students here. And in case students are right at the borderline, please give them a promotion, okay? I'll tell him that, okay? Those who are still quiet, please, okay, don't be shy. I can tell you 90% of the chance you actually know the answer, but you just don't want to be, you know, outspoken, and I can understand, okay? We'll give you opportunity to shine when you come to oral presentation, okay? And so today, I think the pre-lab is due at 5. Are you able to handle it now? Ladies and gentlemen?
Yeah.
You
I had one question about the mechanism though.
Okay, sure.
So do we do 2 different net reactions for each of the different steps and then do the mechanisms for each of them? Or do we just do the Grignard reaction for the mechanism?
There is only one mechanism for Grignard, okay?
Okay, so we don't have to do the formation of the Grignard reagent?
No.
Okay.
Yeah, forming the Grignard reagent itself, you dissolving it. No, that kind of mechanism is too complicated, okay?
Okay.
I can tell you, we can write arrows here and there, and then we have dots here and there, okay? It's actually, yeah, actually, it's not easy when you talk about orbital shearing for this kind of, that's very complicated. I'm willing to drop it, yeah.
How lenient are you guys going to be on this that lab report that we turned in? Because you know what? I was rereading over my lab report yesterday, and I don't know. Like, I wish I had an extra day or so to do it or whatever. But yeah, it's probably not my best work. So
You're talking about your Aldo.
yeah, it's so hard doing a theoretical lab report. Like, because there's no way that was a wild ass lab report. Like,
You don't feel related, huh?
no, I don't. I almost feel like I'm cheating. You know what I mean? It's like a weird feeling.
It was like over a month ago that we did it.
Yeah, and then we had to think about some of the stuff we did over a month ago. Man, that was the most hardest thing I've ever done. That was, wow, that was very difficult. I don't even know. I can't even tell you. Like my first lab report, I knew that I got an A. This one, I don't know what the hell. I probably got an F. So
I see.
it's just so unconnecting. Like it's not like.
It's
Man.
not your baby. I know.
That was wild. I don't ever want to do that again.
Well, you will do that for another 3 reports. That's
Yeah, I know, it's
another 2
unfortunate.
reports. Yeah, sorry. I cannot offer any improvement over this. Okay, that's the problem. We all encounter very difficult situation. I can tell you, I'm very lucky to be able to offer my help. With my capability, I'm able to stretch my maximum and help my students. Okay, although it's probably not the best to you, but I have tried. Okay, can you imagine those professors who have small children at home? Can you imagine how difficult their lives are now? Okay, taking care of small children because they cannot go to school, and you have to lecture from home, etc. And you got to take care of them. It's not easy, okay? Okay, so we all experience very difficult stage of life now. Okay, it's not our fault, okay? We only need to try our best, okay? And once we finish or we go over this hill, we are a more capable person. I guarantee that, okay? Just look at life this way, okay?
Mm-hmm.
All right, ladies and gentlemen. Is there anything else I can answer? Yeah.
In our balanced reaction, are we supposed to say which one is the dominant one?
I already give you the answer, right?
No, I know that, but we're not supposed to put that in our balanced reaction. We just write out the balanced reaction, right?
You know, ideally, yes, ideally, you want to draw this too. At least you have to know how to translate the chelating model or the Falking arm model. Okay, well, maybe I will check that when I do the report grading. For the pre-lab writing, you still want to list 2.
Yeah, I did that. I just didn't put which one would be the dominant one.
You don't have to know at this stage. It is when you show me the report, you want to show me your prediction, and then you want to show me, you know, the drawing, okay? And actually, there will be questions in that direction, yeah. Asking you, is this model working? Or is this model working? Or both working? Or both fail, okay? You're gonna show me, okay?
Mm-hmm.
Yeah, in the report writing, I can tell you this is coming up. This is a typical Chem 420 question, okay? You may not believe it because I've seen the final exam in the past. It's a typical question like this, okay?
This was our last pre-lab, right?
Yes.
The one that's good because I don't have no more space.
Yeah. Well, I'm showing you one example of final exam questions, okay? We give you a molecule like this, and then we don't show you product. Okay, now show me your prediction. Which isomer should be preferred according to either this model or this model, okay? We ask you to write down what should be the major product in the 3-dimensional drawing. Yeah, this is very, very typical in 420. Okay, this kind of question is very typical to 420. Okay. All right.
No,
No, not yet. All right.
Yeah, that makes more sense. That makes a lot more sense. Okay, cool.
Cool. All right. All right, ladies and gentlemen, are you able to submit the pre-lab at 5? Can you respond to me?
Yes.
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 Okay, let me check the dots. Anyone here? If not, if you're not able to respond in voice, if you want to text, I feel better. Okay, I just want to make sure people register the message without any problem. Okay, thank you for responding. Okay, and before we say goodbye, this is all.
Yeah.
All right. All right. I'll see you next week. Okay. Someone's.
Yep.
Hold on. Someone's writing. Andrea, are you responding to me? Andrea? Okay. I'll say goodbye then. All right. See you next Tuesday. Bye-bye.
All right. Bye.
Thank you. Bye.
Bye-bye.
Bye.
Bye.
Bye.